couple of things. So obviously, last time we started talking about gases, which obviously is the state of matter where, pretty much everybody has sort of completely broken apart from one another. So obviously, as they are flying around, there's a number of collisions that occur. And as those collisions are occurring, it does affect things like pressure. So the more collisions that we see, the more pressure we would expect to occur. Obviously, if we were to sort of lower the collisions or the amount of collisions that are occurring, we would see a decrease in the pressure. So when we talk about pressure, there are certain sort of units that we very commonly in this class come across in terms of pressure. A couple of those units are atmospheres, ATM, millimeters of mercury, mmHg, and also torr. So there are obviously, as we talked about last time, other units of pressure, but these are really the three sort of common units you very often will sort of come across. There is a relationship between these three things. First off, the millimeters of mercury is the same as a torr. In a sense, it's basically a one-to-one relationship between those. So if you need to convert between millimeters of mercury and torr, or torr and millimeters of mercury, pretty much it's the same number. You just change the units. It's a one-to-one relationship in terms of conversion. Now, between atmospheres and each of these guys, there's basically the same conversion because they do equal each other. So one atmosphere is 760 millimeters of mercury, and that equals 760 torr. So as we talked about last time, basically that 760 number is an important number. It is the one that you will use to really go between these different units. And depending on sort of where you start as to, how you should use the 760. So for example, if we are in units of atmospheres and we want either millimeters of mercury or torr, we're going to actually multiply by this 760. And again, that would give you a torr, which again is the same as a millimeter of mercury. And vice versa, if you have a millimeter of mercury or torr, you would then divide by the 760. And that would get you to atmosphere. So again, very common conversion going really to atmospheres from either of those units. We do see a lot. We then started sort of talking about some of the gas laws here that we see. And when we talk about sort of gas laws, there's really sort of three variables that we look at. There's pressure, volume, and temperature. And in some of these gas laws, we keep one constant, maybe vary the others. So we first started out with really Boyle's law. And Boyle's law is P1V1 equals P2V2. And here, this is at constant temperature. And the units of pressure here can be any units you like, as long as they are the same on both sides. And that also goes for the volume here. They could be any units you like, as long as they are on the same on the both sides. The relationship that we saw with Boyle's law was sort of an inverse relationship, which basically means as one goes up, the other one goes down. So if we basically decrease the volume, that's going to give the gas molecules a much smaller area to fly around in. And what that's going to really do is increase the number of collisions. As it increases the number of collisions, we would expect the pressure to go up, as we see there. And then obviously vice versa, we would see the pressure start to go down if the volume goes up. And the opposite is true in that case. We sort of increase the volume, and that allows a lot more room for those gas molecules basically to fly around. The result of that is we would expect a lesser number of collisions to occur. And because the collisions are going to occur at not as high of a rate, we will see that pressure drop. So Boyle's law, one goes up, one goes down, is sort of the relationship that we saw there. We also talked about Charles' law, which is V1 over T1 is equal to V2 over T2. This guy here is at constant pressure. Now, in this situation, volume can be any unit you like, but temperature, as we talked about on both sides here, does need to be in Kelvin. So we saw that graph where, no matter what gas you're dealing with, as it comes back to the temperature line there, it hits minus 273.15, which is basically absolute zero. So always a pretty safe bet there that if you are doing something that involves a gas law and you're doing something that involves temperature in a calculation, it should absolutely be always in Kelvin. And again, as I talked about the other day, even if the problem sort of gives you the temperature in Celsius and even asks you to provide the answer in Celsius, sometimes people do miss that one because they think, well, again, they gave it to me in Celsius. I need to give the answer in Celsius. I can leave the temperature in Celsius, and that's incorrect. You do need to convert it to Kelvin, put it into the gas law, and then convert it on the back end of the calculation back to Celsius. The relationship that we see here is basically as one goes up, the other goes up. So as the volume goes up, temperature goes up. And as the volume goes down, the temperature goes down. And the reason for that is we're in a situation where we want to maintain constant pressure. And if we increase the temperature, we would expect the gas molecules to start flying around a lot faster. If they are flying around a lot faster, we would expect a lot more collisions, and thus we would expect the pressure to start to go up. So because we want to maintain that constant pressure, what happens in a Charles law situation is as the temperature increases and our gas molecules start to fly a lot faster, the volume actually adjusts, and the volume will adjust in a way to be able to maintain the same number of collisions. And because the number of collisions really don't increase, because we increase the volume, gave everybody a lot more room to fly around, we do see that the pressure is able to remain constant. Same thing happens in sort of the opposite direction. If we lower the temperature, we would expect that the gas molecules would be flying around a lot slower. And if they are flying around a lot slower, we would expect, again, less collisions to occur, and that would cause the pressure to start to come down. Because we want to keep it at constant pressure, what we do is, even though the gas molecules are moving around slower, we bring the volume down. And what that does is now they don't have to travel as far, and the rate of collisions will basically remain the same. And that is, again, how we're able to maintain sort of constant pressure. So in sort of a Charles law situation, what we have happening is the volume is really adjusting either up or down to basically keep the rates of collisions constant. And that is how we're able to maintain basically constant pressure. And that's a little bit different than what we saw with Guy Lusik's law, which is very much related here. P1 over T1 is equal to P2 over T2. And this would be at constant volume. So what we have here is the same situation. We do have temperature. So obviously they does need to be in Kelvin. But what happens in this particular occasion is as the pressure goes up, so does the temperature. And as the pressure goes down, so does the temperature. And it's because in this situation, the volume is pretty much locked into place. There's no way for it to go up or down. It's got to maintain exactly where it is. And what that means is if we again increase the temperature in this situation, we will see those gas molecules fly around faster. And again, in this case, the volume is not going anywhere. So we will see the rate of collisions start to increase. And as the rate of collisions increase, we will then see the pressure start to go up. And vice versa, if we lower the temperature, our gas molecules again will be flying around a lot slower. which means it's going to take longer for collisions to occur, and we will start to see the rate of collisions start to come down. And because there's less collisions, we will also see the pressure come down. So sort of Guy Lusick situation, we don't have that volume that will adjust in a way to maintain the pressure. And that's why we do actually see a change in pressure here. We then also talked about our good friend Avogadro. That's a very badly written A. Avogadro's law, which is V1 over N1 is equal to V2 over N2. And this one is actually at two constants here. It's at constant pressure and temperature. And volume here on top can be any unit you want. N here is actually the moles of the gas. So again, in chapter 7, we discussed converting things to moles and what moles are, but that is what N represents, which is moles. And sort of the relationship here is as the moles of a gas sort of increase, so does the volume and so forth. So they kind of work sort of together. We finished up, I think, on kind of putting all these guys together. And, when we look at these sort of gas laws here, what we do see is kind of a before and after condition here. There's two pressures, there's two volumes, maybe there's two temperatures. And putting all these together, we do get the last gas law that we looked at the very end there, which I believe was the ideal gas law. And that was PV is equal to nRT. And obviously this one, as we talked about last time, and as you can see here, is different than all the other ones, as it's really not like a before and after type of situation. We really here, when we use the ideal gas law, have one pressure, one temperature, one volume, and so forth. So we don't see those kind of two pressures, two temperatures, and so forth. Also, though, the most restrictive out of all of the gas laws here in terms of units. So when you do use the ideal gas law, the pressure absolutely has to be in units of atmospheres. So if you're going to use the ideal gas law and you're in some other unit, you probably need to use this conversion up here to convert it to the proper units. Volume has to be in liters. N, which is moles, has to be in moles. And T, like every other gas law, does need to be in Kelvin. And really the reason that all these guys have to be in these particular units is really because R is what is referred to as the gas constant. It is a value and a constant number that you always have. And again, you should always keep that in the back of your mind that you do always have R, although it may not always be sort of given to you per se in the problem. And very often it's not even mentioned in the problem. But again, is a value that you sort of always have to use if you need. And the value of R that we typically use, 0.08206. Again, sometimes people will round this to 0.0821. Again, you can use either of these numbers. I think I might have mentioned last time, I personally usually use the top number because that's just what I learned back in the day. But the units that are associated with the gas constant are liters times atmosphere on top, Kelvin times mole on the bottom. And that is exactly why all these other guys here need to be in these units, so that when you multiply or use R in the calculation, all the other units will cancel out correctly. Also, good news is you usually are always given R. So you usually always have this value. And that means that you could kind of just look at the units with it. And that should help you remind yourself as to what the other units need to be. Any questions on any of that stuff there that we talked about last time? Now, Also, we sort of talked about last time that, there's a number of different gas laws, as we can see here. We're going to add a couple more here probably today. Uh, a really good way to work out problems is, as we sort of did with a couple of those last time, is really, kind of take the information from the problem, pull it out, sort of label it. And what I mean by label it as a pressure, label it as a volume, label it as a temperature. And a lot of times, if you just simply take out all the numbers from the problem and sort of label them, you will almost have sort of the gas law staring at you and kind of point you in the right direction. So sometimes it's very helpful in sort of picking which gas law you should use if you just kind of pull out the information and label them. The other thing that we talked about again is there's a lot of rearranging that happens in these gas laws. So you want to make sure that you understand how to properly rearrange these guys. And again, just a quick way that you could do it. There we go. If we have an equal sign and you really need to move something across the equal sign, as I talked about last time, you can kind of think of everybody as like fractions, kind of like top and bottom, if you will. So if something's on the bottom over here and you need to move it to the other side, it ends up on top, and vice versa. Obviously, it ends up on the bottom if you started there, and opposite way this way as well. So, it's kind of almost a quick way to kind of move things around. It's really based on the math operation of either multiplying or dividing, but just really quickly, if you look at an equation, like say that one right there, which is our P1 T1 is equal to P2 T2. And let's just say that I wanted to solve for P2. I would need to move this guy to the other side. Again, he just ends up over there. That gives me T2 P1 T1 would equal our P2. So again, just sort of a quick way to rearrange these guys, because it's a very common problem that people have is the rearranging part, and then also putting in the correct numbers, like the first temperature, second temperature in the proper location. Any questions on any of that there? Okay, then let us continue on with where we were, which was here, I think. Okay, so as we just talked about there, again, the ideal gas law is a pretty big sort of gas law. It is, again, sort of used for really a one and done type situation. Again, really no kind of before or after situation. A couple of other important things in terms of the ideal gas law and just gases in general there are some relationships that can be very helpful as we go through sort of gas laws and stuff like that. The first relationship is what we see here on top, that experiments have shown that 1 mole of any gas will equal 22.414 liters at STP. So this is actually a conversion factor that 1 mole, again, of any gas will equal 22.414 liters. And again, you can use it like a conversion factor as 1 mole over 22.414 liters, or 22.414 liters over a mole. And again, you could use this actually in place in some cases of putting things into the ideal gas law. So the important part, though, is you could only use this relationship at what is known as STP. So let's talk about what STP means. STP stands for standard temperature and pressure. So if somebody says, hey, this is at STP, which is a common sort of question and stuff like that, you may think, well, that's not a lot of information, but it actually is a lot of information. It is actually giving you two values. It is giving you a temperature, which is 273 Kelvin, and it's giving you a pressure of 1 atmosphere. So if somebody says basically, we ran this experiment at STP, or what is the volume at STP. They're actually giving you a temperature and a pressure when they say STP. Again, the temperature is 273 Kelvin. The pressure is 1 atmosphere. So if you are at STP, and again, you can do one of two things. For example, if you were trying to solve for a volume, you could use this relationship, but again, it has to be only at STP. Or you could use something like PV is equal to nRT and solve for volume, which would be nRT over P. And again, here, if they said at STP, you would put in for the temperature 273, you would put in for the pressure 1 atmosphere, and then obviously whatever your moles would be, you would put in there. Or alternatively, you could use the moles of what you have, and again, use that conversion factor as a mole is 22.414 liters will give you liters. This will also give you liters, and those two numbers will be exactly the same. Again, the rule is the 1 mole is 22.414 is only at STP. Ideal gas law you can use for STP conditions and any other conditions you like. So more universal, the ideal gas law. This guy up here, again, very specific situation. If it is not 273 Kelvin and 1 atmosphere, then you cannot use that relationship. Any questions on that? You absolutely would have to go into the ideal gas law. This is actually how we kind of get the value of the gas constant. If we put everything in, solving for R from the ideal gas law, the pressure would be 1 atmosphere at STP. At STP, 1 mole of gas would have a volume of 22.414 liters, and it would have a temperature of 273. And again, this is essentially where we get our 0.08206 value from doing that. So 2 important things: what STP means, which again means a temperature of 273 and a pressure of 1 atmosphere. And again, you can use what's sometimes referred to as the molar volume of the gas, but it is at STP. 1 mole is 22.414 liters. All right, so why don't we try one here, see what you come up with. Calculate the pressure in atmosphere exerted by 1.82 moles of SF6 in a vessel with a volume of 5.4 liters and a temperature of 69.5 degrees Celsius. Take a few minutes to see what you come up with. Okay, let's take a look here and see how to approach this. So we really do want to approach this one kind of like what we approached everything else. And again, I would recommend just pulling out the information. So obviously here we are looking for a pressure. They do give us moles, which is N. We do have a volume, which is 5.43 liters. And we also have a temperature that's 69.5 degrees Celsius. So again, you could probably pick up that the ideal gas law here would be the one that you want to use. Plus, if you think about Boyle's law or Charles' law or any of those other ones, we don't have like 2 pressures, we don't have 2 volumes or 2 temperatures. We basically just have one of everything. That means also you always have R, which is that 0.08206 number, which is liters, atmosphere, Kelvin, mole. So again, if we just think about PV equals nRT, which is the ideal gas law, we are looking for P. We do have V, we do have N, we do have T, and again, we always have R. So that allows us to know really where to go with this. Remember that we want to make sure when we do use the ideal gas law, units are really important. So obviously we're solving for pressure, so we don't have to worry too much about that. Volume needs to be in liters, which it looks like it is. Moles should be in moles, which it is. R is the gas constant, so it doesn't change. Temperature should be in Kelvin, which it is not. So we do have to do a conversion here to convert our temperature into Kelvin. So the temperature of 69.5 plus a 273, I believe, gets us 342.5 Kelvin. And now we do have the temperature and the units that we need. So what we want to do again is rearrange this. And even though this is really not written as a fraction, you could think of it as a fraction over 1, if you will. But basically what we need to do is move our volume to the other side, which means it is going to end up down there. And that gives us P is equal to nRT divided by V. What we're essentially doing is dividing volume to both sides when we do that. Any questions on that rearrangement there? Now that we have it properly rearranged, we want to put everybody in the correct spot. So up on top, 1.82 moles, our R value. Our temperature converted to Kelvin, all divided by our volume here, which was 5.43 liters. In terms of units, everybody's going to cancel out except for the one that we need, which is good. The moles on top here and moles on the bottom here will cancel. Kelvin on top and badly written Kelvin there on the bottom will cancel. Liters on the bottom and liters on top will cancel. It leaves us with atmospheres, which is good because that is a unit of pressure and what we're looking for. So 1.82 times 0.08206 times 342.5 divided by 5.43. Looks like we end up with a 9.42 atmospheres as our pressure here. Any questions on the calculation?
Professor, on the for the moles to cancel out, you always have to make sure you put in the ATM over the mole, right? On the R.
Yeah, so the R, because it's a constant,
Yes.
these units are always this. So it's always liters on top times atmosphere on the top, and always on the bottom is Kelvin times mole. So that's the arrangement so that everything else would properly cancel out correctly. Yep.
Okay, thank you.
You're welcome. Other questions? Okay. Also a reminder again, kind of out of chapter 7 as well. You're not always going to be necessarily, for example, given, things in moles, and very commonly you're sometimes given things in grams and you need to convert to moles. So a reminder that it is the molar mass from the periodic table that would allow you to, get that value into moles. So for example, if we had, let me see if I got this where, let me go back. That's right here. So let's just say we wanted to know the, we'll do volume, why not? What is the volume of, say, 32.0 grams of, we'll just do krypton gas at, say, 26.5 degrees Celsius and a pressure of, we'll just do 772 torr. So if we have this problem, again, if you kind of pull out the information here, we're looking for a volume. We have grams here, not moles, but we do need to get them into moles, which would be N. We have the temperature here, which is 26.5 degrees Celsius. And we also have a pressure here. So again, if you kind of looked at this problem here, this should also lead you to the path of the ideal gas law, which is our PV is equal to nRT. Again, we have a pressure, we're looking for a volume, we have a temperature, we always have R just like we did before because it is a constant. Again, with those units. So what we see here is we don't really have moles, but we do have grams. So this is again where we would go to the periodic table to figure out the molar mass of krypton. So if we look at krypton and we look at what it says there ish, I think it's 83.80. The molar mass comes from the number on the bottom. That again is the molar mass. And what that means is there are 83.80 grams of krypton in 1 mole of krypton. And we could use this as a conversion factor. And that's what we would want to do here to get us into the correct units. We would take 32.0 grams of krypton. We would divide it by the molar mass that we get from the periodic table. Here, the 83.80 grams per mole of krypton. Again, the grams cancel. Calculator here. 32 divided by 83.80 gives us 0.382 moles of krypton. So now that we converted it into moles, we now have the moles that we need. We still need to do a couple other things on this particular one. But again, a reminder, this is out of chapter 7, converting grams to moles using the molar mass. And again, it's a really important thing to know how to do. We do have it in moles. We do also need to convert our temperature into Kelvin in this particular problem I made up. Let's see. So we would want to add 273 to that guy. That gets us to 99.5 Kelvin. And our pressure is not in the right units either. It's in torr. And remember, it needs to be in atmospheres here. So we do need to take 772 torr, and we need to divide by that 760 number. That way the torrs cancel. And that gets us 772 divided by 760, gets us like a 1.02 atmospheres. So now what we've done is we've got our units converted from grams to mole into the right units. Our temperatures has now been converted to the right unit, and our pressure has now been converted to the right unit. Now we are okay to actually use this equation because everybody's in the correct units. Here we would want to solve for volume. So again, PV equals nRT, although it's not a fraction, you could think of it as a fraction. And we would then want to send pressure to the bottom over there. And that would give us volume is nRT over P. Putting in our numbers now, 0.382 moles. Again, R is a constant, so you always have this number. And again, the appropriate units to go with it, liters times atmosphere, Kelvin times mole. Our temperature, which we converted to the proper unit as well, all divided here by our pressure, which was also converted to the proper unit. This way, the moles here will cancel the moles here. The Kelvin here will cancel the Kelvin here. Atmospheres and atmospheres will cancel. That leaves us only one unit left, which is liters, which is good because that is actually what we're looking for. So 0.382 times 0.08206 times 299.5 divided by 1.02 gets us a 9.20 liters as the volume here in this particular case. Any questions on any of those steps. Again, it may require several conversions to do these problems correctly, because really our ideal gas law has very specific units. And again, this conversion here, which again comes out of chapter 7, is a really important conversion. Again, using the molar mass from the periodic table to convert our grams to moles. Any questions on that particular one there? Okay. All right, so continuing on, let's see where we ended up now. This way. Just did. Continuing on with our sort of gas laws, we're going to add a little bit to it here. And there is actually, a situation where perhaps we could have changes in all three of the variables, pressure, volume, and temperature. So if we take really the ideal gas law, which is what is done here, and solve for R, because R is a constant, you can set each of these sides equal to each other. And in most cases, the moles of the gas don't really change. The only way the moles of the gas would change, you open up the lid, let the gas out. So most of the time, if it's in a container and it's a gas, you usually don't open up the lid or anything like that. So the moles usually remain constant. So we get this gas law here that we could add to our list, which is P1 V1 over T2 is, I'm sorry, not over T1, not T2. Got ahead of myself there. P1 V1 over T1, that's counting, there you go. And that will equal P2 V2 divided by T2. So the deal here in terms of units are pressure, it does not matter, again, as long as they are both the same on both sides so that they cancel. Same thing with the volume here, as long as they are all the same on both sides, it's okay. Much like every other gas law, though, the temperature still needs to be in Kelvin. This is what is sometimes referred to as the combined gas law, because it pretty much deals with everybody. Also, the one, again, that does give people a pretty difficult time in terms of rearranging. So, again, that sort of crossover move might be beneficial for you to rearrange things. But again, if you do have difficulties rearranging equations, you may also want to take some time to, just practice that aspect of it, sort of rearranging and, making sure that you can do that correctly. So why don't we try one and try your skills here? So let's take a look at this. Consider a sample of oxygen gas at 27 degrees Celsius with a volume of 9.55 liters and a pressure of 2.97 atmospheres. If we change the pressure to 8.25 atmospheres and we increase the temperature to 125 degrees Celsius, what will be our new volume of the gas? So take a few minutes here and see what you come up with. Again, pull out the information, see what you got going on, properly rearrange the equation, and we'll talk about it here in just a second. Okay, let's take a look here and kind of see. So again, I'm just going to kind of do what we've been doing. I'm just going to kind of pull out the information. So clearly I got a temperature that is 27 degrees Celsius. I have a volume that is 9.55 liters, and I have a pressure that is 2.97 atmospheres. My pressure then gets changed to 8.25 atmospheres. I also changed the temperature to 125 degrees Celsius, and I am looking for a volume. So again, here, if you look at this, you could kind of really see the combined gas law, hopefully staring back at you. P1 V1 T1 is P2 V2 T2. Again, it really doesn't matter which ones you call ones and twos, as long as you keep the information together. But since these guys came first in the problem, we'll call these ones and these guys twos here. We then want to double check units. Remember, really in this sort of formula here, the only unit we really should check for sure is temperature. And we do see it's not in Kelvin. As long as the other units are the same, which we look at the pressure, they're both atmospheres, so they're okay to go. We obviously are solving for a volume, which means we will end with liters here. But we do definitely need to convert this guy out to Kelvin. So we're going to add a 273 to each of those guys. Yeah, I'll squeeze it in here, I think. Then that gets us a 273 plus a 27. That's a 300 Kelvin. And a 125 plus a 273, which would be a 398 Kelvin. All right, so now we got everybody here in the correct units. We want to then make sure that we rearrange this equation properly. So as we can see from above, we are solving for, in this case, V2. And V2 is on top, which is good, which is where we need it. But it does also mean we need to move over both P2 and T2 really to the other side. So again, if you just take your T2 here, and since it's on the bottom there, it will end up on the top on that side. And if we take our P2 on the right there, it's on the top, it will end up on the bottom over here. And when we do that and we rearrange it, we will end up with basically nothing changed on the left-hand side. Everything's the same. We just then moved our P2 to the bottom. And to the top there, we moved our T2. Throwing this away. And that left us just the volume on the other side. And again, that's sort of a quick way that you could really rearrange it and sort of get it correctly. At this point, we're ready to put our numbers in. And we again want to make sure we do get the correct numbers in the correct location, which is sometimes a problem. So we're actually looking for T2 up on top. So that should be 398 Kelvin. Our P1, which was 297 atmospheres. And our V1, which was 9.55 liters up on top. On the bottom, we're looking for P2, which is 8.25 atmospheres. And our T1, which is actually here, which was 300 Kelvin. Any questions on the rearranging or putting the numbers in?
Professor, on the Kelvin, isn't it 2.7, 273.5?
It's
Or do we just, or do
yeah,
we just,
most people, myself included, will just use 273.
oh, is that okay to then just use 273?
It
Isn't
is,
it
it is,
0.5?
it is for me. The correct number is really 273.15. Most of the time, this gets kind of lost in the rounding part at the end. And that's why most people will just kind of use the 273. So
Okay.
for me, it's perfectly good to use 273. If you want to use the 0.15, you can. There's nothing really wrong with it. Actually, it's truthfully correct. But in most cases, like I said, it oftentimes will get kind of rounded off. And that's again why people will kind of just stick with the 273. So either one's perfectly fine.
Okay, thank you.
You're welcome. Other questions? Okay, then I'm gonna grab my calculator here and see what we ended up with there. So again, we're gonna multiply everything on the top there. So 398 times 2.97 times 9.55. Remember to hit equals at this point. Then I would personally divide by the first number, which is 8.25, and I personally would hit equals again and divide by the last number, which is 300, and hit equals. And that then leaves us with, go up here, 4.56. In terms of the units, the Kelvin on top and bottom cancel. The atmospheres on top and bottom cancel. Again, that leaves us liters as our units here, really based off of the other volume, which was liters. Any questions on that one there? So the combined gas law here, again, is one where, people do struggle with the rearranging of it and kind of putting the correct numbers in the correct location. So, just be careful as you rearrange it. And then secondarily to that, when you actually do go to solve it, be careful that you do put sort of, the right numbers in the right location. And what I mean by that is, it's very common, for example, people will do like T1 on top and T2 on the bottom in this situation, and kind of really kind of flip those numbers around. So that's the combined gas law that, again, basically covers all the three variables together, the pressure, the volume, and the temperature sort of changing together in that situation. All right, the next thing that we're going to talk about is, in most cases, when we do deal with gases, they oftentimes do come as basically mixtures of gases, mixtures of different gases. And because of that, we get what is really referred to as partial pressure. So what we mean by that is, for example, if we had sort of a straightforward situation where we had a container, and basically the only container in, or the only container in there, the only gas in that container is, say, gas A. And gas A is the only gas that's flying around in that particular container, which means all the pressure that we associate with that container, which is the total pressure, would be a result basically of just gas A. It's the only guy in there that's really banging around and, banging into things. But if we did have a mixture of some different gases in the same container, so for example, let's just then say we had a second container over here, and in this container we had gas A, we had gas B, and obviously we have gas C here. We'll add to it, why not? Gas C. Now, in this particular container, everybody is flying around, A, B, and C. And in this particular case, they are each basically contributing to the overall pressure that's happening in that container. As gas A hits the wall, for example, it's going to cause some pressure. Then gas B will hit the wall, gas C will hit it. There'll be these collisions that are occurring as a result of all three different gas molecules. The result of that is, when we talk about the total pressure of this particular container here, right there, the total pressure in this container would be the result of the pressure of A plus the pressure of B plus the pressure of C, basically all added together. And because they each contribute to the overall pressure, they're not responsible for all of the pressure. They are what are referred to as partial pressures. So this would be the partial pressure of A. This guy here would be the partial pressure of B. This guy here would be the partial pressure of C. So because not one gas is responsible for the overall pressure that we see in that container, and they all sort of contribute to it, they were referred to as partial pressures, because when we take them all together, by adding them all together, that gives us basically the total pressure of that container. Any questions on that there? Now, there's a couple of good things. How do we sort of calculate partial pressures? Well, for the most part, we calculate partial pressures by using the ideal gas law. So we can use PV is equal to nRT. And the goal here would be to solve for P for each gas individually. So we could take each gas that's flying around, like gas A, gas B, gas C, and rearrange it and solve for it. So we would do the pressure of A is equal to nRT over V. The partial pressure of B would then be nRT over V. The partial pressure of gas C would be nRT over V. Now, remember, this is the same ideal gas law that we used previously, which means, again, we do have to watch units as we talked about. We need our atmospheres, we need our liters, that obviously is moles, and our Kelvin, along with the gas constant. The good news is, though, when we think about these calculations, which are basically in this particular example, 3 separate calculations that we would do, and that obviously then we would add up all the p values together. When we think about the gas here in this container, there's a couple of the things that are the same for every single gas that's flying around in there, because every single gas is flying around in that container. The volume is the same for all gases, which means if you went to this ideal gas law, the volume number here for every single one would be the same. The other thing is this container is most likely sitting in a room where the temperature is probably not changing all that much. So the temperature as well for all of those guys would be the same. Which means, again, if we come here to our temperature, that is going to be the same for everybody. And we already know that R is a constant, which would be the same for everybody. Which means, typically speaking, when you need to solve for the partial pressures of each gas, really the only thing that's usually different is the number of moles. So again, here, the number of moles typically will be different for all 3 of these, but everything else will be the same. Any questions on that there? So put that page here. So again, we would basically just solve the ideal gas law for each of the gases individually. And when we do get those pressures, we basically would add them all together, and that would give you the total pressure of that mixture of gas. Why can we think about each gas flying around and do 3 sort of separate calculations for them? One question you might have is, are they not interacting with each other? I would think makes sense that, we have multiple gases sort of flying around in here, A, B, and C. Are they not interacting with each other and affecting each other? And that is really where the ideal part of the ideal gas law comes in. When we talk about an ideal gas, one of the things that makes something an ideal gas under sort of normal conditions, kind of everyday conditions here, is there is an assumption that under these conditions, if the gas is behaving ideally, there's really no interaction between the different gases, which means having multiple gases flying around in the same container will not affect the other gases that are flying around in the container. And that is why when we do a problem like this, where we definitely have 3 different gases flying around, we could almost envision that each of these gases are in here by themselves. So, A is flying around by itself, B is flying around by itself, C is flying around by itself. And there's really no interaction between the 3 different gases in this container in an ideal gas situation. So that's, kind of the one idea when we talk about ideal gas is one major thing that makes something sort of an ideal gas is the idea that even though there's multiple gases flying around in the same container, they basically will not really interact with each other. So we could almost think of them as being in that container by themselves. And that's why we're able to do basically 3 individual ideal gas law problems with 3 gases that are actually in the same container, because again, their behaving was referred to as being ideally. Any questions on that? Okay, so why don't we try one here? We got 5 grams of helium and we got 5 grams of neon. They are in the same container, 2.5 liter container at 27 degrees. We're looking for the partial pressure of each gas. So we're looking for the partial pressure of helium. We're looking for the partial pressure of neon. And we're also looking for the total pressure. So you should end up with 3 answers here. The partial pressure of neon, partial pressure of helium, and the total pressure. Let me give you some information that might be helpful. If you go to the periodic table and you look up neon, underneath neon, you will see basically 20.18, which means the molar mass of neon is 20.18 grams per mole. And if you look at the periodic table for helium, you will see 4.003, which means the molar mass for helium is 4.003 grams per mole. Okay, so give it a go here. Again, 3 different answers: partial pressure of helium, partial pressure of neon, and taking everybody into account what the total pressure is. Here, this is again a mixture of gases like we were just talking about. So think ideal gas law and see what you come up with. Okay, let's see how you're doing here. So again, really in this situation, we got 5 grams of helium, we got 5 grams of neon. They're both, borrow this green here. They're both in the same container, basically flying around. So remember that this automatically kind of tells you it's a partial pressure situation. We know that the volume and temperature of this container will be the same for each of them. We could go through and kind of pull out the information. We do have 5 grams of helium. We also have 5 grams of neon. We also have 2.5 liters, which is a volume. We have 27 degrees Celsius, which is a temperature. And remember, we know we're probably going to use the ideal gas law here. We have volume, we have temperature, we're looking for a pressure. We have grams, which can get us to moles. So it does mean we are going to use, kind of P equals nRT. Again, we're looking for pressure. We have a volume, we have a temperature, we always have R. And again, we're not directly given the moles, but we can use the grams to get there. So we definitely know that. So that will be R is our 0.08206 liters atmosphere Kelvin mole. We want to make sure unit wise here, liters are exactly what we need for the ideal gas law. So that's good. R is obviously okay. We do need to add our 273 here to our temperature. Now looks like a 300 Kelvin. So now that is good. So the first thing that we want to do is we want to convert our grams into moles here. Again, we would go to the periodic table and find the molar mass. In this case, it's helium. If you look under helium, it says 4.003. And again, we will use that as a conversion factor, 4.003 grams on the bottom, moles on top. And if we do that, we're basically taking 5 divided by 4.003 gets us a 1.25 moles of helium. We'll do the exact same conversion, but except we'll use the molar mass for neon from the periodic table, which is 20.18 grams per mole. We take 5 divided by 20.18 gets us 0.248 moles of neon. Any questions on that calculation there? At this point, we now have these guys, which are N, right, in our ideal gas law. So now we do have N, we have V, we have R, we have T. Remember that even though these guys are in this container together, we're going to kind of assume that they are in there by themselves, which means we're just going to do two separate calculations, one for helium and one for neon, and that will give us our partial pressure. So the first one is going to be, we're going to rearrange this and solve for P. And that would give us P for helium is nRT divided by V. Our N, which is our helium, which is 1.25 moles. Our R, which is our constant, 0.08206. Our temperature is 300 Kelvin, all divided by our volume here, which is 2.50 liters. Again, moles will cancel, Kelvin will cancel, liters will cancel. Going to leave us atmospheres, which is a unit of pressure, and what we're looking for. So if we do that, we end up with 1.25 times 0.08206 times 300, hit equals, divided by 2.5. We end up with a 12.3 atmospheres. So what does this number represent? This number represents what is known as the partial pressure of helium in this case. We're going to do pretty much the identical calculation. The only thing that's going to be different here is the moles. Remember that because they're in the same container, the volume and temperature will be the same for both of them. So the partial pressure here of neon would be our nRT over V. We want to make sure we use neon's moles here, 0.248, are going to be the same. Temperature going to be the same because they're in the same container flying around. And volume will be the same because they're in the same container. Same canceling out's going to occur here. That is going to again leave us with atmospheres, which looks like we end up with 0.248 times 0.08206 times 300 divided by 2.5 gets us a 2.44 atmospheres. This number represents the partial pressure of neon in this mixture of the two gases. Remember that we're also looking for what is the total pressure. In this case, the total pressure is made up of all the gases that are present. So that would be the partial pressure of helium plus the partial pressure of neon. And that would give us a 12.3 plus a 2.44 atmospheres. Gives us something like 14.7 atmospheres as our total pressure. Really the contribution of both helium and neon in this particular case. Any questions on that there?
So Professor, anytime it asks for total pressure, then all you do is combine whether it's 2 or 3 gases?
Exactly.
Okay.
Yeah. So however many gases you have, as soon as you are able to figure out what the partial pressures of each of those gases are, and if they're all in the same container, simply just add them all together. And that will give you your total pressure.
All right, thank you.
You're welcome. Other questions? So this is one common way to figure out partial pressures, which is essentially just doing a ideal gas law individually for each of these gases. Again, that's basically what the ideal part of it means, even though they're in the same container. You know, there's really no interaction between them. So we could kind of almost assume that they're in there by themselves. Another very common situation that occurs where we get a partial pressure situation is sort of experimentally when we do an experiment and how the gas is collected. So for example, if we do this experiment, which is maybe the experiment this week, potassium chlorate, you add a little bit of MnO2, which is a catalyst. You heat this up, you're going to generate some oxygen gas here. This is a closed environment. This oxygen gas has got nowhere to go, but kind of through the tube. And previous to this, you set up basically a container that was filled completely with water. You put it into really a bucket of water here as well. So what happens is as the oxygen gas comes in, basically the water inside the bucket basically goes out. And what ends up happening is you get this area in the bucket here, which kind of looks empty. But it's really not empty. It's actually where your oxygen gas would end up as it comes in here. So as the oxygen gas comes in, the water comes out. It appears empty in the container at that point, but that is basically filled with the oxygen gas. But the problem with this is the way that we're collecting this gas is with a lot of water that's present. And just as a result of the heat of the reaction, when you heat up water, in addition to the oxygen that you're collecting, you get a little bit of water that comes up in here as well. And you get what is referred to as water in the gas state, which is also known as water vapor. So you actually end up collecting two gases in this case. You collect the oxygen gas, which is really what you're interested in, but then you end up collecting some water vapor, which is basically the gas version of water, which you're really not interested in at all. So what you end up getting is really a partial pressure situation. The total pressure in this case would be the pressure of the oxygen gas, which is actually what we're looking for, plus the partial pressure of water, which again is referred to as the vapor pressure of water. The good news is if we wanted to really just figure out the pressure of the oxygen gas, which is what we're interested in, we could rearrange this by solving for the oxygen gas, which means we could take the total pressure and subtract it from the vapor pressure of water. In a laboratory, where's the total pressure come from? Well, you read the barometer. It's basically the room pressure there. So you read the barometer. Where does the vapor pressure of water come from? It comes from typically a table. So you can look up a table and find the vapor pressure of water at different temperatures. And you could subtract the two and you would get the pressure of, sometimes referred to, the dry gas, the O2 in this particular case. So in a general speaking way, the total pressure is the pressure of the gas you're interested in plus the vapor pressure of water. So this is another sort of way that we could do a partial pressure situation. How do you know it is the situation? Usually there's a couple of words that pop up in the problem that kind of tells you it is the situation. It will sometimes say it was saturated with water vapor, or it may say it was collected over water. Either one of this terminology basically means you need to use this equation and rearrange it into this equation to basically get the pressure of the dry gas. It's sometimes referred to dry because we're subtracting off water's contribution to the pressure. We're not really interested in the water's contribution. It's really just a side product of how the gas was collected. So we usually kind of need to correct for that and basically subtract it off. So let's take a look at a problem that involves that. If we have a sample of oxygen gas that's saturated with water vapor at 30 degrees Celsius, the total pressure is 753 torr, and the vapor pressure of water at 30 degrees Celsius is 31.824 torr. What is the partial pressure of the oxygen gas? So again, a couple of words that we see here that tells us we're in that situation, saturated with water vapor, tells us, okay, the total pressure in this case is the pressure of the gas we're interested in plus the vapor pressure of water, which means in a lot of cases, I would need to go look this up in a table. But in this particular case, they were nice enough to give me that value. This value, again, would normally be found in a table where you would find that value based on the temperature. You would go to the table and look up 30 degrees Celsius. And in that table there at 30 degrees Celsius, you would see this number listed. So the total pressure was also given to us in the problem. So we have the total pressure, we have the pressure of the hydrogen gas. That means in this case, we could rearrange for the pressure of oxygen, which is what we're looking for. Total pressure minus the vapor pressure of water that comes from a table. That means we would take 753 torr minus the value that was from the table, which is this number here, 31.824 torr. Again, you do want to make sure they're in the same units. And in this case, they are. And we take 753 minus 31.824, gives us a pressure of the oxygen of 721 torr. They do want the pressure in atmospheres, so we do need to do that conversion. 760 torr is 1 atmosphere, so we would divide that by 760, and we would end up with 0.949 atmospheres. And this would again be pretty much the pressure of the dry oxygen gas, which is what we were interested in this question. So this is another sort of partial pressure situation that occurs anytime you collect a gas that water's involved. You will get an added bonus of water, which is not really a bonus because you really don't want it. So you have to do really this sort of correction where you subtract off the vapor pressure of water, which you find in a table, from the total pressure to get the pressure of the gas that you're actually interested in, which in this case was the oxygen. Any questions on that there? Okay, we're kind of done, and we're almost done with this chapter. We have a couple of slides to look at, but we'll stop here for now. We'll talk about a couple of things. This is, I think, the last chapter before your next exam, which is about a couple of weeks away, I believe. So because of that, I think we will do a quiz next week, and we will do a quiz on some of the earlier chapters, which is like 6 and 7. So we will do it on naming. So everything involved in nomenclature or naming at a 6, we'll do it on. And in terms of 7, we will do it on balancing equations. So we'll keep it to those 2 topics, just to help you start reviewing, hopefully, if you haven't. But we'll keep it to just these 2 topics out of here. We will do it on Wednesday next week, which is some date, whatever today is. Today's the 6th, I think. So it's at the 13th, perhaps. We'll do it like last time. We'll be through Canvas. You'll need to use Proctorial. We'll have a short lecture, and then for the last part of the lecture time, you'll be expected to take the quiz. And then obviously you'll go off to wherever you need to go off to at that point. That also means that in a couple of weeks, the online homework is due. So make sure that you are doing that and progressing through that. Do not wait to the last minute, because it's probably a lot to do in the last minute. You might not finish it. So make sure you're taking care of that mastering chemistry stuff as well. Any questions on any of that there?